In 2023, a forensic engineering team attempted to read an original Apollo computer module using a modern FPGA emulator. Despite a perfect reconstruction of the official schematics, the modern reader returned a stream of garbled, nonsensical data. The team was trying to extract the exact original flight logic that guided humanity to the lunar surface. Modern digital systems process abstract, weightless code. They lack the native logic to interpret the physical, immutable behaviors inherent to mid-century hardware. To navigate space, NASA relied on core rope memory. This was a system of tangible software, where the zeros and ones possessed actual mass and physical dimensions. Once the flight logic was finalized, the entire memory module was permanently entombed. Engineers cast the delicate copper wiring inside a dense, heavy block of epoxy resin. This potting process was a strict structural necessity. The hardware had to survive the violent acoustic vibration of the Saturn V launch and the relentless ionizing radiation of translunar space. Because the software was frozen in solid plastic, it was strictly unalterable in flight. Half a century later, modern emulators aren't reading a file, they're attempting to interface with a fossilized artifact. This is Standard Erasable Magnetic Core Memory, or RAM, the baseline computing technology of the 1950s. This architecture relied on a destructive readout. To read a data point, the system forced the magnetic core into a zero state, erasing the information as it was retrieved. Management of these cores required a coincident current addressing system. By sending half currents down intersecting X and Y grid lines, engineers could target and flip one specific core without disturbing its neighbors. The race to solve the destructive readout problem carried massive economic stakes during the Cold War. Anne Wang at Harvard invented a pulse transfer controlling device that automatically restored the data after every read cycle. This breakthrough triggered intense intellectual property warfare. IBM eventually paid a historic $13 million settlement to MIT to secure the rights to the 3D array memory architecture. The Apollo program circumvented this volatile read-write cycle. They utilized core rope memory, a read-only architecture where the ferrite cores functioned as sensing transformers rather than storage cells. Moving the flight logic into a permanent, physical configuration traded alterability for absolute stability. Creating this permanent memory required translating MIT's complex mathematical schematics into exhaustive physical wiring diagrams. Manufacturing took place at the Raytheon plant in Waltham, Massachusetts. They recruited local textile and watch factory workers, women possessing the extreme fine motor precision necessary to weave the memory by hand. The data was hard-coded by physical routing. A sense wire passing directly through the center of a magnetic core registered as a 1. If it bypassed the outside of the core, it read as a 0. By threading dozens of wires through a single core, they achieved a data density of 72 kilobytes per cubic foot, nearly 18 times denser than standard read-write memory of the era. The NASA quality control standards were punishing. If inspectors discovered a single misthreaded copper wire late in the assembly process, the entire 8-week manual build was scrapped. The logic required for orbital rendezvous and lunar descent was compiled using the ancient mechanics of a textile loom. During the Apollo 11 lunar descent, this hardware faced a catastrophic system stress test. A rendezvous radar switch was inadvertently left in the wrong position. This caused a hardware mismatch between 15-volt and 28-volt reference signals. The resulting phase drift generated approximately 6,400 spurious hardware interrupts per second, starving the computer's processor and triggering the infamous 1202 program alarm. The physical entombment of the code saved the mission. Because the core rope memory could not be overwritten or corrupted by the interrupt storm, the priority scheduling system remained stable enough to shed low-priority tasks and maintain control. The primitive, unalterable nature of the woven hardware functioned as the primary fault-tolerant mechanism, preventing a fatal system crash during the lunar descent. Decades later, the 2023 forensic restoration team finally identified why their modern reader had returned garbled data. They found an undocumented hardware bug in the original design. The inhibit wires occasionally generated enough stray current to trigger unrelated magnetic cores on the opposite side of the module. The original MIT programmers were fully aware of this physical misbehavior. They wrote the Apollo flight software to anticipate and navigate around the broken hardware logic. To read the data, the modern engineers had to intentionally rewrite their flawless FPGA code to perfectly replicate the flawed physics of the 1960s. The Apollo software was a permanent genetic flaw trapped in epoxy. Legacy infrastructure permanently forces modern technology to adapt to its past.